Okay, going on with some examples. Number 30 in this section is, well, it has the look of a path function for how far something has gone over time. It's the initial s that makes me think that. Okay, so let's break this down. We have an exponential function, yes, but we also have a constant multiple here. So here's the exponential, which is going to involve some chain rule here. And then here we have a constant multiple. Okay. So the derivative, we have 5 times. Because it's an exponential with a base other than e, we have the log here, so that's log of 2. Now we have the exponential function itself. And now we have to have the derivative with respect to the variable t of that stuff inside. Okay. So carry along all of this. And I'm going to think of this as the derivative with respect to t of t minus 2 to the power 1/2. So at this point, since we've been doing derivatives for a little while, we can think of that derivative as 1/2 over times 1 over the square root of t minus 2. So that's 1/2 times t minus 2 to the negative 1/2. Okay, I need to do that a few times each year, and then I get used to it, and I just write it this way, kind of on automatic pilot. So, reviewing here, we had to use the chain rule for the function inside the exponent there. Okay, next. So, reading the problem, we see that we have here a percentage. Let's see. This is a percentage of people of a, you name it, age, who will die in any year. Now, because this is an exponential function with a positive exponent, we know that it's going to have a shape something like this. I mean, sooner or later, it's going to go up like so. And so what is this telling us? Well, the percentage of people who are old who are going to die in a given year is greater than the percentage of people who are young who are going to die in a given year. Okay. So the important observation here is that it looks like every other exponential function. I don't know what the scale is here, but I know that the general shape is like this. And so we have old people, young people, and then the other thing that I want to call your attention to here is that we are asked two different questions. One, we have the function values, and two, we have the rate of change at each of those places. So it's like saying, here's one function value. We're going to read that from the vertical axis. And then there's also the rate of change. And that's, we can visualize as the slope of a tangent line. And these are not the same thing. Okay, well, let's start with finding these function values. So we have t and p of t, and the only rational thing to do here is to use a calculator to plug in. And also, before we go any further, we should note that we expect the rate of people dying to be much greater than the rate of, at an advanced age, than the rate of those deaths at a small age. Okay. Okay, so here are the values I got from running these numbers through the calculator. Rounded to 6 places. Okay, so I look at these and I think, wow, really 2 or 3% of people aged 25 might die every year, and 28% of 50-year-olds I never noticed. I think I would have done. And then I realized, okay, this says percentage, so this is the percentage. About 3% of 1% of 25-year-olds die in a given year. So that's what, 26 out of, I think, every 10,000. That makes more sense. 1/4 of 1% of 50-year-olds, so maybe 1 out of every 200. And 3% of all the 75-year-olds. Okay, so then we need a derivative of this function to answer the next bunch of questions. Okay, so this is an exponential. So first we have this constant multiple times the original exponential function, and then the derivative of the stuff inside. So we have another constant multiple, which is this one. And when I take its derivative, what I have is times 0.0957. So now I'm going to multiply these two constants together, and here's what I get. Okay, so now I can plug in the same values for t into the growth rate function. Okay, and here are the answers that I get from that. Okay, so growing very slowly for 25-year-olds, but growing at a rate that we could probably see with the naked eye for 50-year-olds. Okay, and get a load of how it comes out for 75-year-olds. I had to take a good look at my numbers here. Okay, here we have 0.3% for 50-year-olds, growing at a rate of 0.3% per year, but growing at a rate of almost 400% for 75-year-olds. So that means that for 76-year-olds, there will be about 4 times as many of them dying as 75-year-olds. How about that? Okay, did we answer all the questions that were asked? Okay, first, interpret the answers. So, for 25-year-olds, the gotta backtrack here a second. Let's see, the likelihood of death in a given year is 0.026%. And the death rate is growing at 2 or 3 thousandths of 1% per year. Okay. And then likewise for all of the others. And then there was one other question at the end. Are there any limitations of this formula? Well, what do you think? Does it all end somewhere? We don't even have to have a death rate for 200-year-old people because there aren't any. So I'll let you come up with a statement for situations a little less outlandish than that. I think that's the end of this part.